everyone, welcome to this new Atlanchim Pharma webinar. So after a webinar last June on Redal, a versatile reducing agent, and another webinar in December on Tosmic, a powerful reagent in the synthesis of heterocycles, the title of this new webinar is Applications of Desmartin periodinane in Organic Synthesis. You have here the chemical structure of this reagent. But before I get started, I would like to remind you of a few points. In March, we published a new scientific letter on the hydride reagents with the second part of an overview of the reducing power through recent examples. Like all the others, this new Atlanchim Pharma scientific letter is available on open access on our new website at this address, just right here. Last month, in May, we published a post on the LinkedIn in our fortnightly The Minute of Chemistry on Desmartin's reagent as presented in this slide. We will come back to this example later in the section of the oxidative fragmentation of 1,2-diols. And in fact, this original and surprising reactivity of Desmartin's reagent gave us the idea of this webinar. Desmartin's reagent is widely used to oxidize primary alcohols to aldehydes and secondary alcohols to ketones. But the Desmartin's reagent can also have unexpected reactivity. And we will be looking at this aspect together this afternoon. So you have on this slide the summary of the different points concerning Desmartin's reagent, which we will discuss through recent examples, mainly from total synthesis of various natural products and also from medicinal chemistry. Few general points about this reagent. This hypervalent iodine reagent here was developed in 1983 by the two American chemists James Martin and Daniel Dess. It is a stable white powder, commercially available and quite easy to handle. In comparison to chromium and DMSO-based oxidants, this periodinane has a number of benefits, such as milder experimental conditions, room temperature, neutral pH, quicker reaction times, greater yields. This reagent is also highly soluble in organic solvents, as we shall see later. Also, it is preferable to use non-anhydrous solvents, such as weight dichloromethane. With this reagent, you have also easier workups. A simple treatment with an aqueous solution of sodium hydrogen carbonate to neutralize the acetic acid formed during the oxidation reaction, and then a treatment with an aqueous solution of sodium thiosulfate to reduce excess of Desmartin's reagent. You have with this reagent a high chemoselectivity, a high tolerance to sensitive functional groups. This reagent has also a long shelf life under anhydrous conditions, which is an important point. However, Due to its potentially explosive nature, its industrial use remains difficult. For the preparation of the Des-Martins reagent, it turned out that the use of oxone instead of potassium bromate in aqueous sulfuric acid was more convenient for many reasons in order to obtain the 2-iodoxybenzoic acid, also known as ABX. Oxidation of the 2-iodobenzoic acid was complete in 3 hours in water at 70 degrees with 1.3 equivalents of oxone. Regarding the acylation of ABX with acetic anhydride, to obtain the Des-Martins reagent, Ireland proposed in this reference here using a catalytic amount of para-toluene sulfonic acid instead of a large amount of acetic acid. For each transformation, as you see, the yield is high and 100 grams per batch can be prepared. However, Des-Martins reagent has sometimes a capricious behavior. So Stuart Schreiber, in this reference, has made a significant contribution to a better understanding of the reactivity of this reagent. It is therefore crucial to obtain a pure, crystalline, anhydrous Des-Martins reagent. With this in mind, Schreiber developed here an efficient procedure. ABX was heated at 85 degrees in a mixture of acetic anhydride and acetic acid for at least 1 hour after dissolution was complete. Then the reaction flask wrapped in aluminum foil is left to stand for 1-2 days at room temperature to allow crystallization of the Des-Martins reagent. During product isolation, exposure to the atmosphere is strictly avoided. The Des-Martins reagent obtained is crystalline and completely soluble in dichloromethane and especially in deuterated chloroform, which is an excellent sign concerning the quality of this reagent. In fact, the reagent contains only a small amount of acetic acid. So, as you can see on this slide here, with these two examples, using cholesterol as a starting material, Schreiber observed that the oxidation rate was greatly increased by adding just 1.1 equivalents of water to anhydrous dichloromethane. And as you can see on this slide, the yield was also better. So to explain this rate acceleration promoted by water, it has been proposed that after a first ligand exchange between water and the acetal group, this first intermediate is formed. A second ligand exchange between the alcohol and another acetal group provided this second intermediate. At this stage, the increased electron donating ability of the OH substituent in place of the acetal may increase the dissociation rate of the remaining acetate ligand, leading to the carbonyl compound following this concerted mechanism. So, in the context of total synthesis, we will now look at a couple of examples where the Dess-Martin periodinane was used to oxidize alcohols, other methods, and reagents having failed. For example, in the final step of an enantioselective synthesis of the C1 C11 fragment of this macrolide, oxidation of this highly hindered OH group was expected to be slower than the oxidation of this primary alcohol. Also, it was pointed out that problems could arise with beta-gamma unsaturated aldehyde moiety here formed rapidly, which in related systems is known to be sensitive to C10 epimerization. In this context, the Dess-Martin reagents gave excellent results. However, complete oxidation could not be achieved even by using 6.5 equivalents of the Dess-Martin's reagent when the reaction was performed at room temperature. The reaction had to be gently heated to 40 degrees for 20 minutes to achieve a complete oxidation of the C5 alcohol. The fully protected C1 C11 fragment was obtained as a single isomer in almost quantitative yield, with no evidence of epimerization at C10. In the synthesis of an N-analog of the naturally occurring malariamycin A, this bicyclic secondary alcohol was oxidized in classical conditions with a Dess-Martin's reagent to afford this ketone in a 70% yield on 20-gram scale. In this other example concerning the scalable process for the synthesis of naturally occurring polyphenols, after addition of around 300 grams of Dess-Martin's reagent to a solution of this alcohol in dichloromethane, a solution of dichloromethane saturated with water was added dropwise during around 1.5 hours. So after completion of the oxidation reaction, saturated sodium hydrogen carbonate solution was slowly added, followed by a 10% aqueous solution of sodium thiosulfate. After extraction, the crude product was directly purified by crystallization to give the desired ketone here in good purity in 77% yield on more than 300 grams scale. In the studies toward the enantiospecific total synthesis of rhodexine A, Dess-Martin periodinane oxidation of this allylic alcohol afforded this sensitive dienone in excellent yield on 10-gram scale. It should be noted that due to the instability of this allylic alcohol towards protic sources, 10 equivalents of pyridine were added to neutralize the residual acetic acid in the Dess-Martin's reagent, as well as acetic acid formed during the oxidation process. During the preparation of 8-rotene, various standard oxidation conditions here were evaluated to oxidize this highly injured alcohol. This secondary alcohol proved to be completely inert to oxidation, leading only to the recovery of the starting material. Fortunately, the classical treatment of this alcohol with Dess-Martin periodinane led to its complete conversion to the target tetraketone in excellent yield. In the synthesis of this racemic lignan, this mesodiol was treated with a slight excess of Dess-Martin's reagent to give this lactol as a major diastereoisomer at anomeric position in a quantitative yield. This transformation proceeds by oxidation of one of the two primary alcohols here to the corresponding aldehyde intermediate, which spontaneously cyclizes to this lactol. Also, Dess-Martin's reagent is well known for its usefulness in oxidations of optically active alpha substituted aldehydes, highly susceptible to epimerization when other oxidation conditions are used. So Myers and co-workers demonstrated that the N-smog alpha amino aldehydes, such as this one, prone to epimerization at this center, could be obtained from the corresponding alcohol with less than 1% epimerization using Dess-Martin periodinane oxidation of the corresponding protected amino alcohol as presented here. The tempo-catalyzed oxidation is also a practical and efficient method to produce optically active aldehydes, but in this case does lead to a small degree of racemization, as you can see, between 4 and 6%. Sworn oxidation using 3-ethylamine as a base leads to a degree of racemization around 10%. As presented on this slide, oxidation of this N-protected amino alcohol derived from tryptophan with Dess-Martin's reagent proceeds in excellent yield in around 4 gram scale without notable racemization here at this center. As you know, in organic synthesis, handling sensitive or unstable aldehyde intermediates is always problematic. In this context, Dess-Martin periodinane can offer interesting possibilities. For example, during the course of the preparation of this label intermediate, several oxidation reagents and conditions, uh, such as PDC, PCC, sworn reagent, Dess-Martin periodinane, were examined for the conversion of this primary alcohol to this corresponding aldehyde, but no desired product was isolated. Surprisingly, when this stabilized labeled Wittig reagent here was mixed with alcohol here in dichloromethane at 0 degree, followed by addition of the Dess-Martin's reagent, the corresponding unsaturated ester was isolated in 78%. Obviously, the alcohol here was oxidized by periodinane to this corresponding aldehyde in situ, which then immediately underwent a Wittig reaction with phosphorus ylide here. So in a similar one-pot sequence, in the early stages of a total synthesis of this natural antibiotic, the order of addition of the reagents here is reversed. Treatment of this chiral alcohol with Des-Martin's reagent in dry dichloromethane at room temperature afforded in situ this sensitive aldehyde prone to racemization here at alpha position, as well as a retro-Michael elimination with this protected alcohol in beta position. So when the oxidation reaction is over, direct addition of this stabilized Wittig reagent into the reaction mixture gives the target intermediate here in 82% on almost 4-gram scale. The last points of this webinar concern unexpected reactivities of the Des-Martins reagent. The first point is about oxidative fragmentation of 1,2-diols with Des-Martin periodinane. Sodium periodate and lead tetraacetate are well-known reagents used for the oxidative cleavage of vicinal diols into the corresponding aldehydes and ketones. The oxidation of vicinal diols with Des-Martin's reagent is a highly substrate-dependent reaction without being really rational. You can obtain the 1,2 corresponding dicarbonyl compound or the oxidative cleavage products of this single carbon-carbon bond. For example, in the total synthesis of this natural product containing an unusual reduced furanocyclopentane unit here, treatment of this cyclic diol with Des-Martin's reagent gave this oxidative cleavage product in almost quantitative yield. Only sworn oxidation of this cyclic diol provided the desired hydroxy ketone here in around 82% yield. During a total synthesis of this indole diterpene natural product here, all attempts to oxidize this diol intermediate with Des-Martin's reagent to the corresponding 1,2-diketone failed. Only the CC simple band cleavage product, this one, has been isolated in 58% yield. In the total synthesis of tapsigargine, such oxidative cleavage process was observed on this intermediate here with this 1,2-diol moiety. And Baran proposed a mechanism close to that with sodium periodate via the formation of this cyclic iodo species. In sharp contrast, in the synthesis of marine steroids, this diol intermediate here was oxidized with Des-Martin's reagent using here standard conditions to this hydroxy ketone in a 98% yield on gram scale. And another unusual reactivity of Des-Martin's reagent concerns the chemoselective, chemoselective dehydrogenation of nitrogen-containing substrates, namely benzylic primary amines, to their corresponding nitriles. As shown in this example here, treatment of this benzylic amine with two equivalents of Des-Martin's reagent in dichloromethane at room temperature gave this nitrile derivative in 64% yield. In this transformation, the benzylic amine attacks the iodine atom here of the Des-Martin's reagent to form this complex with a concomitant loss of acetic acid, followed by a concerted intramolecular abstraction of benzylic hydrogen here in red by an acetate group with elimination of acetic acid and this derivative. This dehydrogenation process gives the albumin, which is oxidized a second time by Des-Martin's reagent according the same mechanism to form the nitrile function here. For the final step here, in the total synthesis of this terpene indole alkaloid, oxidation of this indoline unit to provide the desired alpha-beta unsaturated ester motif using these different oxidant conditions felt. Fortunately, treatment of this intermediate with 1.1 equivalents of Des-Martin's reagent in a dichloromethane at room temperature gave the targeted natural product in around 50% yield. Benzylic amines, as we have just seen, but also tertiary amines and related compounds can be dehydrogenated to afford the corresponding albumins following a mechanism close to that described just before. So concerning the previous example, this aromatic amine reacts with Des-Martin's reagent to form this complex with a concomitant loss of acetic acid. Then intramolecular tertiary hydrogen abstraction, so this hydrogen in red, and elimination of acetic acid and this 2-iodobenzoic acid derivative leads to this albumin, which by a simple isomerization of this nitrogen carbon double bond gives the target natural product with here the alpha beta unsaturated ester motif. We will now see some original application of Des-Martin's reagent in a pyrrole chemistry. So the oxidation of pyrroles usually leads to uncontrolled polymerization and or decomposition. However, as presented on this slide, slow addition of this N-substituted pyrrole to a solution of at least two equivalents of Des-Martin's reagent in a weight dichloromethane gives this 5 substituted pyrrololinone in excellent yield. To explain the formation of this pyrrolinone core, it has been proposed that the electrophilic aromatic substitution of pyrrole by Des-Martin's reagent on the here iodine atom provides this Wieland type intermediate, which by rearomatization gives this two substituted pyrrole. Then migration of the oxygen atom of the benzoate on the carbon 2 of the pyrrole and concomitant cleavage of the carbon iodine bond provides this new intermediate. Once formed, this electron-rich intermediate is more reactive than the starting pyrrole, and the electrophilic aromatic substitution is a repeat to form this 2,5 disubstituted pyrrole, which by hydrolysis with a loss of this two substituted benzoic acid derivative gives this pyrrolinone. Finally, reductive treatment with a solid sodium thiosulfate provides the two substituted pyrrolinone here. To better evaluate the chemoselectivity of this oxidation of pyrrole compared to a primary alcohol with a Des-Martin's reagent, this N-substituted pyrrole with this primary alcohol function here was subjected to the oxidative reaction conditions. And interestingly, 5 substituted gamma-lactam with the alcohol functionality still intact was a major product when one equivalent of Des-Martin's reagent was used. As, as an example of this oxidation of N-substituted pyrroles, in the total synthesis of this polycyclic lactam containing alkaloids, oxidation of this pyroazepine here, following the previous conditions provided this intermediate. This crude material was directly treated with an excess of BF3 iterate in dichloromethane, promoting the elimination of 2-iodobenzoic acid, leading to the desired lactam in 81% overall yield on gram scale. To end this section, in the total synthesis of this tetracyclic alkaloid, oxidation of this N-substituted tetrahydroindole here with Des-Martin's reagent in trifluorotoluene gave directly the desired lactam adduct in 60% yield on gram scale. No formation of these two intermediates was detected. To end this webinar, we will look at the use of Des-Martin's reagent as a terminal oxidant in the Wacker process. Oxidation of terminal olefins into the corresponding methyl ketones using palladium 2 catalyst in a combination with copper salts here, and also, of course, molecular oxygen as a terminal oxidant is a well-known transformation called Wacker oxidation. The 2G Wacker oxidation, lab scale version of this Wacker oxidation, exhibits outstanding selectivity and has been successfully applied in a total synthesis of complex molecule. So in 2016, Choudhury and Fernandez published and operationally simple and scalable protocol for the Wacker oxidation using palladium acetate as catalyst and the Des-Martins reagent as a terminal oxidant in a mixture of acetonitrile and water. As you can see on this example, the yield is excellent with this procedure using Des-Martins reagent as a terminal oxidant to oxidize this double bond into this corresponding methyl ketone moiety. The reaction was carried out at a lower temperature compared to the protocol with molecular oxygen. This method, considered as a mimic of the classical Wacker oxidation using palladium acetate as a catalyst and Des-Martin periodinane as oxidant, has been applied to THP derivatives with this here, this double bond to afford the expected methyl ketones in good yields as presented in this slide on this example. Interestingly, no traces of aldehyde were detected, and in all the cases, confirming the high radioselectivity of this protocol. In studies directed towards the total synthesis of miamycin, which is this antibiotic, all attempts at a Wacker oxidation of the terminal olefin of this intermediate here, having here the protected galactose fragment, have failed to provide the methyl ketone. Only the starting material was recovered. Surprisingly, with Des-Martins reagent as a terminal oxidant and palladium acetate as catalyst, this unusual indannone product was isolated in 50% yield with no traces of the desired methyl ketone. So, to explain the formation of this indannone, at first, complexation of the substrate with the catalyst takes place. Then, addition of water occurs to provide this intermediate, which by CH activation gives this cyclopalladium 2 intermediate. Finally, a reductive elimination of palladium occurs to give this bicyclic secondary alcohol here. The oxidation of the secondary alcohol in the presence of the Des-Martins reagent leads to the formation of this indannone. On the other hand, palladium 0 is reoxidized in palladium 2 by the Des-Martin reagent. So I hope this webinar has convinced you of the value of the Des-Martins reagent, not only for oxidation of alcohols, but also for other transformation, as we saw. To conclude, Atlanchim Pharma was founded in May 2004, 20 years later, and over 2,000 contracts completed, covering a large type of chemistry. We have, of course, our favorite reagents. And Des-Martin periodinane is, of course, one of them. Since 2004, we also ensure an important scientific watch, particularly with our scientific letters, with our webinars, and with also the minute of chemistry twice a month on the LinkedIn. We have a strong expertise in synthesis of labeled products, more than the 300 compounds prepared. We have also a strong expertise in isolation and synthesis of API impurities. To contact us, you have here the email and the phone number of Aurélie and Elena, our sales managers. Thank you for your attention. I would like to thank all my colleagues from Atlanchim Pharma and in particular our project managers for the discussions during the preparation of this webinar, and Aurélie and Elena for the organization. Special thanks to Lionel Bidet for all his comments regarding this presentation. Finally, I would like also to thank Luca De Biasi and Vincent Baran for their careful reading and their relevant remarks on the first version of this webinar. So now I think it's open to questions and to discussions. Okay, yes, that is important point concerning water. So during the storage, water must cleave, I think, the oxygen-iodine bond and the resulting non-cyclic intermediate leads to polymeric compounds or dimers that are insoluble in organic solvents, especially in dichloromethane. And I remember preparing Des Martins reagent without taking any precautions regarding moisture. And the reagent obtained was insoluble in deuterated chloroform. And as I say, it is a very bad sign. And this type of reagent was not very effective and sometimes not at all. And that I think it's an important point. And sometimes people have a problem with Des Martins reagent, and it's just a matter of quality of the reagent. Yeah, that's yes, it's what we do when we prepare the reagent, because I think maybe to put an aluminum foil, it could be very important because maybe Des Martins reagent is maybe light sensitive, and especially in this case because you have in the you have in the flask a very high concentration of this reagent, and I think it's better to protect it against light, especially if you left this reagent for 1-2 days for the crystallization. Okay, this question is about one of an example in this presentation of if something general. Okay, maybe we will see that later if you. Okay, another one. Okay, um, with the thin diodes, ABX exhibits very close reactivity compared to Des Martins periodinane. uh, concerning the oxidative cleavage, because in both cases you have the formation of a spiral bicyclic pyonidane. But one point concerning ABX, uh, it has been reported in the literature that in the case of IBX, it is important to add a trifluoroacetic acid, and in this case, you will favor the formation of this spirobicyclic periodinane, leading then to the 1,2-diols cleavage by, of course, oxidative fragmentation. But in the case of Des-Martin's reagent, the mechanism is a little bit different. And I think that the formation of this spiral bicyclic compound is a irreversible reaction. And you go directly to the oxidative cleavage. And in this case, it's maybe the main difference with IBX, but you have in some examples, you have the same behavior of IBX and Des-Martin's reagent. To the best of my knowledge, I don't think so, because hypervalent iodine reagents are not very stable, of course. But I know a special case, and it is a product which was developed by a French company, Simafex, which is from the Gerbeck group. And what they did, they prepare a mixture of IBX. I think it was something like 45% of IBX, and they add isophthalic acid and benzoic acid. And in this case, what they call the stabilized IBX was quite safe and was very stable even during eating. And I don't know if now this such a reagent is used uh, industrially, but I think it's only the only example I have in mind. Well, to be honest, I'm a big fan of Des-Martin periodinane because it's the reagent has a good solubility, especially in dichloromethane. And I remember doing myself oxidation and without any precautions like we have to do, for example, with sworn oxidation to be in anhydrous conditions. And in this case, just to add, Des-Martin as a solid, and it was perfect. And in the case of IBX, the reagent is not soluble, and you have to use most of the time a mixture of ethyl acetate and DMSO or only DMSO. And I have the feeling that you have more side reactions with IBX. For example, one of these side reaction is well known. It's a dehydrogenation of ketone to go to the alpha beta unsaturated ketone. And no, for me the main problem of IBX is its low solubility. Yeah, it's true. I didn't talk about this transformation, but I saw this method, uh, which was published in early 2000s. And when I checked the paper, I found out that this protocol has been rarely used. And I think the weak point of this transformation, because it's a very nice way to get a product, for example, to do after a cursus rearrangement, for example. But you have to use at least 6 equivalents of desmartin periodinane, 3 or 4 equivalents of sodium azide. So I think it's not a very convenient procedure. Well, I don't think that desmartin periodinane is pyrophoric. I know 2 points about safety. It's don't heat, of course, the reagent, and when as a solid, don't try to crush it. You know that could be very dangerous. These compounds are sensitive to heating and to impact as well. So it's but pyrophoric, uh, I don't think so. Well, I don't. Uh, well, I think it's the same, you know, to be honest, I didn't see example of large scale use of desmartin periodinane or IBX, and I think it's just a problem of safety during manipulation. But I don't think it's this the side product, for example, of desmartin periodinane is difficult to remove. You know. Ah, Uh, concerning this point with protocol, I saw a couple examples by Barban and Casey Nicolaou. It's a paper from 1988 where they are doing a very special way to oxidize catechol. If you send me your email, I can provide you with this reference if you want. Okay, thank you for joining us this afternoon for this webinar. If you have any questions or comment, please don't hesitate to let me know, and you have somewhere my email. And the next webinar will take place in early December on a different reagent or methodology, I don't know yet. So have a nice summer break and bye-bye.